Hello, Earth Science students, and welcome to your 8th lecture on sedimentary rocks. So we're moving right along through igneous rocks onto sedimentary. We're not going to study metamorphic actually in this class because that's just kind of a little bit too deep into geology than we need to go. So I am going to present to you a little bit about sedimentary rocks because I want you to understand a little bit about especially how sediments form and weathering and all of those processes. So we're going to get into this today, and I'm going to be moving on from here. Next time, I think we're going to start weathering. That's what's going to be our topic next time. So anyway, this is a stunning picture of Bryce Canyon. It's a national park in Utah, and if you ever get a chance to go, it's quite a spectacular view. And one thing I want to point out here, these are all sedimentary rocks you see here, and the kind of like weird structures that you see all over here. These are all kind of type of weathering, differential weathering. So we're going to learn about how those form next time. But one thing I want to point out here, if you look carefully, you should see all these kind of bedding planes, these lines. Especially back here, you can see it pretty clearly, right? You see like the lines of beds of rocks here. You can see beds of rocks here, right? You can see how this white colored stuff right here you can kind of follow it with your eyes and trace it through many of these little pinnacles here, right? So what is all this stuff? Well, those are all bedding planes, sedimentary beds. Okay, so one thing that's really important about sedimentary rocks is that they form beds. Okay. They form beds like and I mean like stratigraphic beds, so layers. That's how you know a sedimentary rock. Okay, so we did igneous last time. Remember that igneous rocks here, these are the ones that form from melts. Sedimentary rocks are the rocks that are made up of weathering products. And I know that sounds like a weird thing, like what the heck is a weathering product? Well, we're going to talk about that today, and you're going to learn all about weathering products. So they're found all over Earth's surface. Actually, more than 75% of Earth's surface is covered with sedimentary rocks. Most of the time when you look at Earth's surface, you will find sedimentary rocks form kind of a layer on top. So notice that the rocks below, this is a picture of the Grand Canyon, by the way. The rocks below are igneous and metamorphic rocks. We call those crystalline basement rocks. You can see that term used right here, basement rocks. And on top, you have this kind of veneer of sedimentary rocks. So actually, most of the crust consists, by volume, consists of igneous, right, and metamorphic. So this is that kind of gray color that you see there. That stands for igneous and metamorphic, this stuff right here. Okay. However, you see in the little sliver that stripedy color represents sedimentary rocks, and so by volume, sedimentary rocks are not very much of the crust, but by surface area, they're actually quite a lot. So you can see that sedimentary rocks cover a large amount of the surface area, about 75% of the surface area of the crust. Okay, so if you dig down to the rocks underneath, there's always going to be kind of like soil, or often going to be soil on top of the rocks. But if you dig down and get past the soil to the rocks underneath of us, you're probably going to find sedimentary rocks. Okay. Now, a really important thing about sedimentary rocks is that they tell us all about the environment of the past. So that's why they're so important. All the information that we know about what has happened in Earth's history and how the environment has changed and how maybe it was the temperatures were different or the climate was different, knowing, there was an ocean here, there was a forest here at one time, et cetera, et cetera, et cetera. We all know that from sedimentary rocks. So different environments lay down different kind of rocks. Lakes, for instance. Have you ever gone to a lake and or maybe even a better idea, I guess it kind of depends on the lake, but what kind of sediment, you think about this, what kind of sediment do you find on the bottom of a lake, right? Like what is the bottom of a lake like? Well, it can kind of differ. It actually depends on the size of the lake. For example, sometimes big lakes, you might find sand, but smaller lakes or ponds, you might find like mud or silt or something like that, right? So the kind of sediment that gets laid down, it's highly dependent on the environment. So lakes maybe lay down sand, sometimes clay, silts are more common. What about now fluvial environment means a river environment. What kind of sediment do you find on the bottom of a river? So I guess, again, it kind of depends on the river. A slow-moving river, you might find kind of like mud. But a fast-moving river, you might find pebbles or sand, right? Or even cobbles or big boulders sometimes in real fast-moving rivers. In swamps, what's the bottom of a swamp like? Well, it's usually like not something you want to stick your feet in, right? It's usually kind of gross mud filled with a lot of organic matter. Well, you're going to find that swamps are actually the places where you get the most, you get coal produced. So coal is the kind of rock produced from swamp environments, okay? Deltas are filled with silt and sand and clay. Coastal environments, you all know this very well living in Corpus Christi. What kind of sediment do you get in coastal environments? You get sand, right? Off the coast, a little bit out, you'll find coral reefs. Coral reefs, you're going to get different kinds of sediments being deposited there. What kind of? I'll talk more about coral reefs later. Sand dunes out in the desert, right? You get sand deposited. In saline areas, you get saline lakes, right? So these are kind of like hyper evaporative areas where you get inland lakes that are evaporated by the high heat and evaporation out there, right? So anyway, my point to you is that all these different environments deposit different kinds of sediment, and those sediments are going to turn into different kind of rocks, and we're going to be able to tell what the environment is based off of what the rock type is, okay? So for example, corals form a mineral, calcium carbonate, which are built up out of all of the marine organisms, right? So clams and corals and all the little crustaceans and animals, they build their shells out of calcite, and that calcite eventually hardens and turns into a rock called limestone. Sand in the desert environments is going to harden and turn into sandstone, right? And that lets us know, again, what the environment was like. For example, the inside of America, the American interior, North American interior, we think used to be an inland sea at different points. And why is that? Well, it's because, here in Wyoming and in Montana, we find kind of like coastal and shallow marine deposits. Something that you would find at a beach, not at, the Great Plains or something like that. So we get all these indications about how the Earth has changed over the years through sedimentary rocks. Another thing that sedimentary rocks can do is they preserve what the climate was like at the time. I'm not going to get into the details of this because it's pretty complicated, but we can look at the chemical composition of the rocks, especially looking at oxygen, what are called oxygen isotopes, and we can figure out what the temperatures were like during different periods of Earth's history. Okay, so think a little bit now about sedimentary rocks, right? The kind of stories that they tell, because you end up getting almost like a story preserved in the rocks. And now take a look at this. This is, I think, a pretty good example. So these are a very famous set of rocks that we find in the Grand Canyon area. And on the bottom, we find a sandstone, right, composed of pure quartz sand that represents a coastal, almost like a beach environment. Now, on top of the sand, we find a shale. A shale is made out of mud, basically hardened, lithified mud that's gone through a process to turn it into a rock. And so the shale represents a shallow marine, so kind of shallow waters. Basically, what you would find if you were to walk, a couple hundred yards off the coast here. I mean, you all know you can wade out pretty far into the bay, and you might notice it as you get further out. Sometimes you get you can get kind of muddier and muddier soils, or muddier and muddier sediments. So we get kind of like shallow marine, maybe like a few meters, things representing maybe like a few meters of water on top of this sandstone here. Okay. Now, on top of that, we get limestone. Limestone only forms where there have been coral reefs. So this represents a very deep marine environment. Okay, so think about this. At this particular point on Earth that you're standing in right now, you're looking at right now, at first it was a coast. Okay. And how do we know first? How do we know this is first, laid down first, and not the limestone up here? So how do we know that? How do we know that this is the first one, and this is the second, and this is the third? Well, we know because the youngest stuff is going to be laid down first, and then on top of that, the even younger stuff, and then on top of that, so actually, I'm sorry, I might have said the wrong thing. The oldest stuff is going to be laid down first, and then younger on top, and younger on top of that. Okay, so things are going to get younger and younger and younger as it gets deposited. Now, what you see here is a little story. So first you get the sandstone laid down, followed by a shale, which represents kind of shallow water, and then deeper water. So you can see what has happened is that this is a story of a rising sea level. So this particular point on Earth was a beach, followed by kind of shallow marine, and then deeper marine waters. So this is a story of flooding, where this particular part in the continent was flooded by a rising sea. And we all are or a lot of people are concerned about rising sea levels now, associated with global climate change. And that's something that's been happening and many times through Earth's history. So the oceans have not remained stagnant, but they rise and fall and rise and fall. So you can see these different rock layers preserved in the Grand Canyon. It's an amazing place to see sedimentary rocks. And think about this. This is pretty crazy. I mean, you have kilometers and kilometers and kilometers of different sedimentary rocks here preserved here. It's pretty amazing. So you can see limestones, shales, sandstones, limestones. So you can see that all these changes between sandstones, shales, limestones, et cetera, et cetera, et cetera, shales, sandstones down here, it all represents the rising and falling of the oceans. So a rising ocean we call a transgression, a falling ocean level we call a regression. And all these transgressions and regressions, rising and falling sea levels, are recorded by sedimentary rocks. Okay, so that's just kind of introduction of all the stuff, just some examples really, of all the stuff that sedimentary rocks can tell us and how we can figure out what the environments were like at the time. But let's talk more about like what is a sedimentary rock. So sedimentary rocks are, again, made up out of weathering products. So what the heck is that? So weathering products are sediments of different kinds. There are three types of sediments. I have A, B, and C. The first type are kind of just fragments of shells, rocks, or minerals that are broken off of the bedrock. So up here you see this is the bedrock. This is actually attached to the crust of the earth still. But all this stuff that you see here, right, this is all sediment that has, just kind of piled up at the base of this bedrock. So this bedrock has weathered away, and it's created this huge what's called talus slope at the base. And this is all sediment. It's all sediment. So sediment's just the loose, broken off rocks and minerals that collect, okay? That's the most common type of sediment. And this type of sediment is called clastic. Okay, this is clastic sediment. Okay. The next type are shells and the fragments of marine organisms. So I know this is kind of crazy to think, and it doesn't go along with our intuitions, but shells of marine organisms build up over time, and they actually form a very important source of sediment. And it's not just like the visible shells. So here you can see actual like visible shells of different marine organisms in here. It's not just that. It's also like little tiny plankton. Like the bodies, most of it actually is this little bodies of planktonic organisms that are in the ocean columns. So you can imagine above the ocean, not above the ocean, but above the ocean floor, you have a couple kilometers, right, of water. It's kind of crazy to think about it, but the oceans are, on average like 4 kilometers deep. So it's 4 kilometers deep, and through that 4 kilometer, column of water, you have a lot of plankton living in there. And over time, those little plankton bodies, they die and they fall to the ocean floor, right? And they start to collect on the ocean floor. And I'm talking about like just microscopic material. And over the course of a year, maybe 1 millimeter of material collects at the bottom. But over 1,000 years, you have a whole meter of material collected at the bottom. Over 1,000,000 years, you have a whole kilometer of material collected at the bottom. Okay? So it really doesn't take that much time before you have a lot of sediment generated by the bodies of little planktonic organisms. So even if you just have a millimeter of buildup every year, millimeters real tiny. It's like thick as your fingernail. That's going to be enough to build up, a kilometer in 1,000,000 years, which 1,000,000 years is nothing for Earth. There's been how many? 4,500 million years in Earth's history. So it's not very much. Next is C. Oh, we call this kind of material, by the way, biochemical material. We call it biochemical because it's biogenic, right? Biogenic means generated by life. Okay. The last thing we have here are mineral crystals that precipitate out of water. So, water always has natural water that's flowing over the Earth's surface. Always has some amount of dissolved mineral content in it. Just like, actually just like your tap water, or well water. I don't think people have too much well water out here in Corpus Christi, but probably like at a ranch out and, further out in the boondocks, people have more wells. And, there's always going to be dissolved material in that water. So when that material evaporates, when the water evaporates, that material is precipitated out and it leaves little crystals, right? So these are salt flats you see here. These are the Bonneville salt flats of Utah. And, all this that you see here, this is all salt that's left behind by inland bodies of water. The water evaporates and it leaves behind the salts that were in it. And maybe there was just a little tiny bit of salt in it. Just a little tiny bit. But, over the years, over 1,000,000 years, it builds up until it's very thick, So in order to weather things, we need to have, back up. In order to produce sediment, we need to have weathering, okay? So weathering is a process that breaks down solid rock. Okay, so we have physical weathering, we have chemical weathering. Chemical weathering is the breakdown of solid rock by chemical alteration. Physical weathering is the breakdown of solid rock without changing the chemical composition. So I'm not going to spend too much time on this right at this moment because we're actually going to have a whole lecture on this next time. But I just kind of want to introduce to you the idea. There's this concept of weathering. Weathering is any process that breaks down solid bedrock to produce sediment, okay? And there are different types of weathering processes, and we're going to learn all about those processes in the next lecture. So these are just some examples of weathering processes. You can see how this bedrock is being broken up by something called exfoliation. We're going to learn about what exfoliation is next time. But it basically occurs when magmatic plutonic bodies, such as granite, rise to the surface and there's depressurization cracks. Also, sometimes when magma is cooling, you get this kind of like thermal cracking. If you ever want to know what thermal cracking is, it's like, I don't know if any of you have ever liked to bake, but sometimes when you're baking, you got a nice hot cake comes out of the oven, and it's a beautiful cake, and then it starts to cool, and then it's cooling, and you get this kind of like ugly crack that forms in the middle of it. It happens a lot with cheesecakes. Oh my gosh. I love a good New York cheesecake, but it's hard not to get it to crack. And just to let you know, in case you like to bake, the secret is you got to leave it in that warm oven and let it cool slowly. If you let it cool too fast, you get thermal cracks. Well, the same thing happens with magma, actually. Magma can get thermal cracks as it cools, and if it cools too quickly especially, it gets these thermal cracks that can break the rock apart and make it easier to weather. So other examples, frost wedging, water gets into the cracks of rocks, expands when it freezes and breaks the rock apart. So there's a lot of different processes, and again, we're gonna learn a bit more about that next time. Okay, so clastic rocks, right? Remember this word, clastic rocks, are formed from clasts, right? And clasts are just little pieces of sediment of broken rocks and minerals. Okay, it's just kind of another word for sediment. So we classify sediment in different ways. So we have based on grain size. So we have mud. That's the smallest. So that's less than 1 in 256 millimeters. That's really, really small. Okay. So we have mud. You can't see mud grains. Okay. Mud grains, mud clasts are too small. Very, very small. A little bit bigger than mud, we have silt. And silt, you can maybe barely see it. You could definitely see it if you had like a magnifying glass, but it's pretty small material. Okay. Silt. So the thing like clay, you know what we have a lot of in Corpus Christi is clay. So if you go out and like start digging in the backyard, probably you have a clay in your backyard. And if you get that clay wet and kind of start squishing it between your fingers, you'll notice it feels pretty smooth. Okay, so that's how you know you have clay or mud. Okay, mud and clay are the same thing in geology. Okay, silt is a little bit grittier. So silt is not quite sand, not quite clay. It's too fine grained to see, but it will feel a little bit gritty. Kind of a gross thing that a lot of geologists do is if they want to tell the difference between silt and mud, they'll actually put a little bit in their mouth and kind of chew it up to see if it feels gritty or not. So I've done that a lot. Nobody likes it, but it is a useful tool. The thing that is a little bit coarser than silt, then you have sand. So sand is, I don't even need to introduce sand because you all know what sand is, okay? And then thicker pieces than sand, you get pebbles, which are between 2 millimeters and 64 millimeters. So 2 millimeters is, still pretty small. It's like, as big as maybe the point of your pencil. 64 millimeters, though, it's getting there, It's not quite as big as your fingertip, but cobbles are kind of like stones, this is really kind of too big for a pebble. That's really more of a cobble. And boulders are pretty big things. There's some boulders, right? So anyway, I have some other better pictures too. So this is all about chemical weathering. Again, I'm not going to talk about it too much, but we're going to talk all about these next lecture, talk about all these different processes of chemical weathering. But these are all chemical processes that break down solid rocks to make sediment. Okay. Now, some minerals are very susceptible to weathering. Some minerals are less so. So the minerals that are very susceptible to weathering and break down really easily are these up here. So halite and calcite. Halite you might remember as rock salt. Okay, this is just rock salt. And calcite is, composes. Sorry, calcite is the stuff that composes limestone. Okay, so if we go down here, let me hold on. Let me adjust something really quick. Okay, I'm back. Sorry about that. So I just had to check on something. Okay, so these are the very susceptible minerals up here. Now, something about these minerals is that these are non-silicates, okay? And you'll notice that non-silicates, so I'm just going to put here not silicates. Rocks or minerals that are not silicates are much softer, typically much softer than those silicate molecules, okay? Silicates are pretty tough minerals. Now, I want you to notice something here that's pretty cool about your minerals that are more susceptible, faster weathering versus slower weathering, and less stable versus more stable down here. So this quartz is more stable, olivine is less stable. Do you notice? Look at the progression here of the different minerals. Olivine, very unstable, very fast weathering. Calcium plagioclase, pyroxene, amphibole. I'm going to skip the plagioclases, but olivine, pyroxene, amphibole, biotite, that's a mica, feldspar, quartz. Does that sound like a pretty familiar order to you? So hopefully this makes you recall the order of the degree of interconnectedness among silicate minerals. So you'll notice that those that are very isolated, remember olivine is an isolated silicate structure, pyroxene is single chain, amphibole double chain. The micas, muscovite and biotite are the two-dimensional sheets. Feldspar and quartz are the framework silicates. Remember that you're getting more and more interconnected. Okay. Again, that plays out in the degree of weathering. So olivine gets weathered out very quickly, and pyroxene second, amphibole third, until you get to quartz. Quartz is a very tough mineral. Things like gibbsite and hematite, this is aluminum hydroxide and iron oxide, are also very tough. Clay minerals are also very tough. Okay, so a lot of times when you have a bunch of minerals that are broken out of the rocks, olivine, pyroxene, amphibole, mica, it's all going to get destroyed pretty quickly. And then when the stuff that actually makes it and gets deposited and preserved in the sedimentary rocks are things like feldspar, clay, quartz, and hematite especially. So these ones, let me go click here and erase all the ink on the slide. But this is the stuff right here: quartz, hematite, orthoclase, clay. This is the stuff that really gets preserved and makes it all the way through the weathering process to get preserved in a sedimentary rock. This stuff often gets destroyed too easily. Okay, so moving on, let's talk about how we make a sedimentary rock. Okay, where does sedimentary rocks come from? So the first process here, let me get rid of this thing. The first process is, again, you have to make the sediment. So sediment is developed by weathering. Weathering is just any process that breaks down solid rock into smaller pieces, and those smaller pieces are called sediment, right? We have 6 different sediment sizes: clay, silt, sand, pebbles, cobbles, and boulders. Okay, if they combine to make sedimentary rocks, we give them different names because we categorize sedimentary rocks, clastic sedimentary rocks, based on their grain size. Okay, so transportation is the next step. So you erode the weathered material. Erode means to remove the weathered material. You transport it, and you can either transport by water, wind, or by ice too. Ice is actually a very effective transporter of mineral grains and rocks and sediment. So believe it or not, ice flows. We're gonna have a whole lecture on glaciers. You're gonna learn all about how ice and glaciers are capable of moving sediment. So what's going to happen is that sediment's going to get transported from a zone of erosion, a place where the land is eroding. Usually those are high places, right, where the bedrock is exposed. You usually only get bedrock exposed in the mountains. Okay. Lower topography areas like, Corpus Christi is a low topography area. We don't have mountains. You usually don't have active erosion going on anywhere. All the bedrock is covered up and protected in a way, covered up and protected from the elements by layers of soil and sediment. But places that are high in topography are going to expose those rocks to erosion, and that eroded material forms sediment, and the sediment's going to get deposited in these low-lying areas called basins. Okay, so there are all different kinds of basins. We have different names for the different things. Like this is called an alluvial fan. It's this amount of sediment coming out of like a mountain canyon. This is called a delta, right, where a river is meeting the ocean. We have sand dunes forming in a basin. We have these piles of sediment formed from glaciers that are called moraines. We're going to learn all about moraines in the glacier lecture. But in any case, that material gets brought in from a river or whatever, from wind or ice, and it gets deposited into a basin. So here I'm kind of drawing this line represents the path of that sediment. It comes in from the river. It flows downhill until you get deposited in a basin. And then what happens? Well, the basin starts filling up. So I'm going to make kind of different colored lines here. And this is going to represent the different amounts of sediment coming in. So, you know, we get layer 1 and layer 2, layer 3, layer 4. And what starts to happen is that the sediment builds up, builds up, builds up, builds up, little by little, right? It's going to build up. And imagine as the sediment builds up, what's going to happen? Well, you're going to have more and more overburden pushing down on the sediments, the original sediments here. Okay, so that's going to increase. You can imagine all of the pressure that's building up from the sediments piling up on top of you. And that's going to, so that increases the pressure. So you end up with high P, high pressure. And that's going to cause a lot of changes in the rock, in the sediments. So number one, the first thing that happens is the water is going to get pushed out of the sediment. And the sediments are going to start to get compacted and pushed together. And once pressure builds up enough, there's actually going to be fusion and cementation of the grains. So you're going to get these, you're going to get along the grain contacts, you're going to get kind of like fusion occurring, and the grains are going to start to be sort of like, they're not, I'm not going to say they're going to be melted together, but they're going to be fused together. Okay, so that's going to create like a homogeneous rock that is, you know, it doesn't crumble apart, it stays together, right? Cemented together. Another process that's happening here is, you know, when the water evaporates out, it leaves behind whatever mineral grains were dissolved in the water, and that also plays a role in cementing the grains together, and that's how you get a rock. So you go from weathering and erosion to transport to a basin. The sediment gets deposited in a basin in a low-lying area, and it undergoes this process called lithification, right? Lithification, aka another term for this is diagenesis, and it's going to end up in you're going to end up with a rock. Okay, so just a little tour through the different kinds of rocks that we have, little different kinds of sandstone rocks. So these kinds of rocks, these are the rocks formed from sediments. So the first type are clastic sedimentary rocks. Now these are the rocks that are formed from broken mineral grains, and class, I just explained how they formed, right? So clastic sedimentary rocks are classified on the basis of grain size. Sandstone is made, unsurprisingly, from sand. A rock called a conglomerate is a mix of sand, silt, clay, and everything under the sun. You can see how this conglomerate has pebbles in it, has cobbles in it, has kind of little silt and sand and clay in between. It's a mix, kind of a melange of different things. Okay, so clay, when clay undergoes diagenesis, lithification. Diagenesis is just another word for lithification. Okay. When diagenesis occurs, you end up with a shale. When silt undergoes diagenesis, you get a siltstone. When sand undergoes diagenesis, you get a sandstone. Okay. When you have a mix of well-rounded sediment, you end up with a conglomerate. But if that sediment is angular, we call it a different term. We call it a breccia. And the reason is that conglomerates and breccias form under different environments. So we give them different names based on whether those cobbles are nice and rounded or if they're angular. See how these ones here are more angular compared to, like, the actual cobbles here are more angular compared to these ones are more well-rounded. And that's because these form in like a land, when you have like a landslide. and these form in kind of like maybe a river fluvial environment. Doesn't that kind of just look like the bottom of a stream, right? So that's literally, you know, how some conglomerates form is in fluvial environments. Okay. So those are the clastic sedimentary rocks. The next type of sedimentary rocks, and we have 4 kind of general categories of sedimentary rocks. So it goes clastic, biochemical, chemical, organic. Okay. The next broad category is called biochemical, and biochemical consists of a lot of the limestones. So, you know, like I said, the ocean is filled with little planktonic organisms. When they die, their little bodies, their little skeletons sink to the bottom, and you build up little by little these different rocks. And those rocks are mostly called limestones. So it's really just compacted shells of clams, oysters, snails, and different little, and a lot just planktonic organisms, right? Plankton. And you build up little by little these very thick beds of rock that are made up mostly of calcium carbonate calcite. Okay. The bodies of these little organisms, by the way, are called coccolithophores. I just think that's a fun word. So, now, not all plankton make their bodies out of calcium carbonate. Some plankton make their bodies out of silicon dioxide, SiO2, which is, by the way, the same as quartz. Okay, it's a very hard mineral, and when those plankton form kind of quartz-based rocks, it's called a chert. Okay, so those are chert beds right here. This stuff is actually quite a bit like obsidian. It's like very fine-grained SiO2 glass almost. This is, by the way, also how opals form. Things like tiger's eye form, and a lot of semi-precious gems form in chert beds like this. Coquina is a rock that's actually found in Corpus Christi that's totally made up out of shells, like clam shells and things like that. Not the little planktonic bodies, but kind of the macroscopic shells. Kind of a cool rock. Here's a phosphoriferous limestone. You can see it's made of a mix of calcite-rich mud and shells. Here's chalk. And chalk is actually, I bet you didn't know, chalk is actually a sedimentary rock. And it's totally made up of these little bodies, right, of planktonic organisms. So it's pretty neat. Oh, gosh. Let's erase the ink on the slide here. Why can't I? That's weird. Okay. Whatever. Weird. Isn't that weird? I can't get rid of that. Okay. So then there's organic sedimentary rocks, which consists of coal. Okay. You can also maybe consider oil shale. It's just a rock that it contains a lot of organic matter in it. Okay, so coal, you know, is just ancient organic matter that's been preserved in the rocks. Okay, so it's undergone a process called heat distillation, and it consists mostly of carbon. A lot of the kind of more complex molecules, organic molecules, have been burned off, but the very precious energy-rich fuel is still preserved there. So that's why we use coal as an energy source. We use oil shale, of course, as an energy source. So we also have chemical sedimentary rocks, which basically form by evaporation. So you have things like gypsum and halite. Gypsum, by the way, is calcium sulfate, like that. It's actually calcium sulfate with some H2O in it, 2 H2Os. You have, of course, halite is rock salt here. And other things like travertine, forms from hydrothermal vents producing calcium carbonate, leaving behind calcium carbonate. These are literally travertine, which is a nice rock. Like, people put that in their kitchens, in their bathrooms, in museums, and government buildings. It's a really, really nice rock. Travertine, literally all travertine is it's like millions of years of hard water buildup. Just like all the hard water, like the hard water buildup that you can get like around like your sinks and your bathtub and in your pipes and stuff like that. That's all travertine is. It's just millions of years of hydrothermal, hot spring water flowing through the rocks, and it leaves behind mineral deposit builds up. So kind of cool. Dolomite is also a chemical rock. It's magnesium calcium carbonate. And I think that's all I have to say about that. So just to kind of go back, I'm going to end this kind of final section taking a closer look at clastic sedimentary rocks. Okay, there's a lot that we can learn from looking very closely at the individual class that make up a clastic sedimentary rock. So looking at those individual grains and looking at their texture. So we can learn something from the shape of the grains, from the size, from the composition, and the distribution of different grain sizes. Okay, so we're going to look at each of these. So grain size, the angularity, the sorting, and the maturity. Okay, so we're going to look at each of these in turn. So first of all, let's look at grain size. So when you have a rock, a clastic sedimentary rock that's composed of like pebbles, cobbles, kind of bigger grains, down to sand, down to silt, that is going to be a reflection of the energy of the depositional environment. Okay, so the depositional environment is the kind of, you can think of the environment in which deposition occurred. Okay, so so one way you can think about this is water velocity. High energy water, high energy deposition environment is going to be like fast moving water. Low energy depositional environment is going to be slow moving water. So think about this, for example. Okay, you're at the beach. There's lots of waves. You're in a place with a lot of waves. Maybe you're on like Padre Island, and when you're on the east side of Padre Island, into the open ocean, to the Gulf of Mexico, what's the sediment like there? Well, it's nice sand, right? Nice sand. But if you go on the other side of Padre Island and you go in like the bay in the backwaters where there's not so much wave action, what's the sediment like? It's not nice sand anymore. It's kind of like mud, And so yeah, if you look or keep your eyes open, go into the different parts of the bay, you'll see that places where the water is slower moving, there's not as much tidal flow, there's not as much wave action. You'll see that there's a lot more mud and a lot less sand. Okay, mud is a lower energy grain, or it's a lighter, smaller grain, and it can be deposited in low energy environments, versus sand is a higher energy environment. Okay, so when we find sandstones, we find conglomerates, breccias, it's telling us that was a high energy, high velocity water flow compared to silts and sands and clay. That's a low energy, very little flow and movement in the water in those environments. Okay. Another thing that we can learn is by looking at the angularity of the grains. So when the sand grains or conglomerate grains or whatever have been well rounded, see how this one is kind of spherical and rounded? It means that, think of a rock tumbler. It means that those grains have been really processed and tumbled and moved for a very long time. So they've probably traveled a great distance. They've moved very far from their original source. Whereas when you find something that is angular like this, it means that it hasn't undergone very much transport. So probably the grains of sand or whatever originated pretty close to the source. Sorting tells you a little bit about it's the distribution of different grain sizes. So see how there's a lot of different size grains here? You got small, medium, big size grains, whereas here all the grains are the same size. So this is called well sorted. Okay, well sorted, and this is called poorly sorted. So well sorted and poorly sorted. It's going to be the result from a few different things. One thing is that it can tell you how the grains were transported. So wind is a really good sorter. Wind sorts stuff incredibly well. That's like, sand dunes, for instance, are formed from the wind. And if you've ever gone to a sand dune, you can see that it's all sand, right? There's nothing else in there. It's all sand. There's no clay. There's no boulders in there. It's all sand. That's because wind picks up certain things, and it can't pick up boulders, it can't pick up cobbles, it can't pick up the pebbles, it can only pick up the sand. And so it moves the sand and bounces it along. But the stuff that's like clay and dust, it just blows way out, like way out to sea. Pardon me. I haven't been talking too long today. So wind is a very good sorter. Water is okay at sorting. Ice, though, sorts very poorly. So you'll see that ice deposited material, like when we study glaciers, ice does a terrible job of sorting. It picks up everything from clay to like boulders the size of, VW bugs. So like cars, So besides that, sorting can also tell you how far grains have been transported. So the more kind of processing that grains have undergone, and the more transport they've undergone, and more tumbling they've undergone, it's going to make them more homogeneous in their grain size. So this is also you could think of this as close to source, and this is far. Okay, so this has undergone a lot of transport. This has undergone not much transport. This has undergone a lot of transport. Okay. Finally, chemical maturity. So you could see here, you have a lot of different kinds of minerals. These different things you see in here are supposed to represent the different kinds of mineral grains. This is supposed to represent mica and amphibole and quartz and feldspars and things like that. Whereas this is just quartz that's left over. So when you see something that's totally chemically homogeneous like this, it means that it's undergone a lot of weathering and a lot of transport. Whereas something that is chemically immature, it has a lot of those very grains that are very susceptible to weathering, like even if it had olivine in it. It means that this has not undergone very much processing and transportation. Okay, so it's probably pretty close to the source. So as you go close to the source to further from the source, a few different things happen, right? Close to source, you get small, let me say it the other way around. The closest to source rock that you can get is a breccia. Breccia, remember, is poorly sorted, has a lot of sharp edges, has a different mix of different grain sizes. It's probably chemically very immature. Next are conglomerates, which have undergone a little bit more transport. They're more the pebbles that are in conglomerates are more well-rounded. Sand, right? You get out a little bit further from the source, you get down to sands, and muds are consists of stuff that's really been transported very far. So as you go far from the source, you get smaller class size, more spherical, less angular, better sorted, more mature, and smaller and smaller and smaller material as it undergoes just more and more and more processing and transport. Okay, so here you go. It's that green sand beach at Hawaii. You can remember that olivine is very hard to preserve. So the olivine is probably coming right out of these basalt rocks right here. It's very close to source. Whereas this quartz sand dune here at Sleeping Bear Dunes, this is a beautiful place, by the way. If you're ever in northern Michigan, I really suggest checking out Sleeping Bear Dunes. Quartz is very far from the source. Okay, it's undergone a lot of transport. Okay, just kind of finishing up here on sedimentary structures. I don't want to spend too much time here, but also there's a lot of structures that are preserved in sedimentary rocks. This beautiful picture of ripple marks is very common, and it's pretty cool. You can find ripple. Now you've all seen ripple marks before at the beach, I'm sure, and ripple marks can be preserved in the sedimentary rocks, and it tells you a lot of information. Like, for example, you can see that if the ripples are asymmetrical versus symmetrical. See how we can kind of draw it's symmetrical on either side of this line. If they're symmetrical, it means it was formed by wave action. If it's asymmetrical, it means that it was formed by a flow of water. So it's kind of cool that you can look at sedimentary rocks and figure out what the direction of flow of the water was. Same thing with sand dunes. Sand dunes that are, the sand stones that are preserved from sand dunes preserve all these structures called cross-bedding. So you can see the cross-bedding in here, right? That cross-bedding tells us what direction the wind was blowing, the prevailing direction of the wind when that sandstone was formed. So it's pretty crazy that, you can look at a rock 2, 3 billion years old, and you have a record of what the wind direction was at the time. That's pretty cool to me. I don't want to spend too much on this. Is graded bedding, things like mud cracks. That's pretty interesting. Here in Corpus Christi, you've seen how the soils get dry and they crack out, right? Because the clays have contracted after they get dried out, right? So mud cracks can be preserved in the rocks. Glaciers can polish the rocks and scratch them. This is a very important to the story of plate tectonics. So glacial polish, glacial striations give us a indication of what the direction of glacial movement was and glacial flow at the time. Like I said, glaciers are not stagnant. They're constantly flowing, constantly moving. So by looking at the scour marks, we can figure out what direction glaciers were moving in the past. We also, of course, most importantly, sedimentary rocks preserve a record of past life for us. So here's, just pretty cool fossilized footprints of dinosaurs that are preserved in the rock. And of course, fossils are preserved in the rock as well. So all these things are different information that we get from sedimentary rocks. So I'm going to end right here. I hope you enjoyed the lecture. And I don't really have too much to say, so I hope you have a good week, and we will see you next time.